Hello everyone, welcome to Artistic Atom channel. I'm Fatima and this is part 3 of organic reaction series. In this session we will discuss second type of substitution reaction. So let's get started. So in the previous session we have discussed free radical substitution reaction that occurs in case of alkanes. In today's session we will discuss nucleophilic substitution reaction that occurs in case of alkyl halides. Well, it is not that this particular reaction only occurs in case of alkyl halides. We are studying alkyl halides because these are the substrates which are more favorable to give the nucleophilic substitution reaction. But in addition to this, we have few more reactants which can undergo nucleophilic substitution reaction. Now, before going ahead, let us first understand the meaning of this term nucleophilic. So when I use this term nucleophilic, it consists of two subterms. First term is the nucleo and second term is the philic. Where nucleo stands for the nucleus and philic stands for the loving. When I say nucleus, it consists of a positive charge. So which species will get attracted towards the positive charge? Well, absolutely right, negatively charged species. So these nucleophiles are the negatively charged species and they get attracted towards the positively charged substrate. This is what is called as the nucleophilic substitution reaction. And we know this term substitution where one group substitutes the other group present in the substrate. So this is how actually nucleophilic substitution reaction occurs. So here we have alkyl halides about which we are going to study in today's session. There are three types of alkyl halides that we have: primary alkyl halides, secondary alkyl halides, and tertiary alkyl halides. Primary alkyl halides always undergo SN2 reaction, that is nucleophilic substitution reaction, which is bimolecular. We will don't worry, we will discuss about all these in further slides. Now, this tertiary alkyl halides, they undergo SN1 reaction. In case of secondary alkyl halides, they depend upon the conditions, and depending upon the right conditions, they undergo either SN1 reaction or SN2 reactions. We will discuss about them also in further slides. Now let us first understand SN2 reaction mechanism in detail. This term SN2 or the abbreviation SN2 stands for substitution nucleophilic bimolecular. Well, we know this term substitution. What is the meaning of this term? Also, we understand the meaning of this term nucleophilic. Now let us understand what is the meaning of this term bimolecular. Well, bi means two, molecular means molecules. So there are two molecules involved in the rate determining step. This means if I take out the rate law for this particular reaction, I will get second order reaction, because the rate of reaction is dependent upon the two substrates or the two reactants that are involved in this reaction. Now, this is how actually SN2 reaction happens. Here we have the substrate, which is a primary alkyl halide. On this particular primary alkyl halide, we have this nucleophile which is going to attack. Well, when I say nucleophile, as I discussed earlier in the previous slide, that it is a species with a negative charge. We can see that this is a species with a negative charge. So this is our nucleophile and this is the substrate. As we can see in this substrate, this carbon carries positive charge. So this is the nucleus to which this negative charge gets attracted towards. So this negative charge is going to attack on this particular carbon atom which is positively charged over here. Okay, it has a partial positive charge due to the presence of bromine atom which is partially negatively charged. Now, as you can see in the image, this OH minus is attacking from the back side. Now you might be having this question, why not this attack is possible from the front side? Well, the reason behind is this. As you can see, this Br is also negatively charged and this OH is also negatively charged. So since they both are negatively charged, it is very difficult for OH minus to attack from this side, because negative charge repels, because the similar charges, they repel each other. Hence, the attack is not possible from the front side. Now this attack is easily possible from the back side because there is not more steric hindrance. What do you mean by the term steric hindrance? Steric hindrance means when we have more bulky groups attached on the carbon atom. Due to these bulky groups, the possibility of this OH attacking on this particular carbon decreases. Hence, usually we prefer primary alkyl halides in order to do the SN2 mechanism, where we have our nucleophile attacking from the backside. Now, as this nucleophile attack from the backside, there is a transition state that happens. Now, what do you mean by the term transition state? Transition state is a state where there is simultaneous bond breaking and bond formation of OH minus, as you can see over here. This means the Br is simultaneous, the carbon and Br bond is simultaneously breaking, whereas carbon and OH minus bond is simultaneously forming. So this particular stage is called as what? Transition state. Now, as soon as we move ahead from this transition state, this Br leaves because it is a living group. So this Br leaves our substrate and this OH attaches itself to the carbon atom. As soon as this OH attaches itself to the carbon atom, this is what we get at the end. Okay, as you can see over here, earlier the configuration of this particular group was this. All the H were on the left hand side. Now, as you can see, they all are on the right hand side. If we put the proper bonds, that is the dash bond and the wedge bond, you will understand how their configuration is completely changed, or we can say the better word for this is that it is completely inverted. So whenever our OH minus attacks in SN2 reaction, it results in the inversion of configuration. What do you mean by the inversion of configuration? Since it is a backside attack, all the groups, they move upside or the on the other side or the opposite side, because there is need of space for this particular group to attach itself to the carbon atom. So we can conclude that in case of SN2 reaction mechanism, there is inversion of configuration that happens. So remember that SN2 reaction is a reaction which occurs in a single step. There is no slow or fast step. Okay, there is just one step that is involved in this reaction. Okay, and it is the fast step. Hence, there is no formation of an intermediate. There is just one transition state that forms, and immediately this transition state get converted into what? Our respective product. Now, when this attack is happening, the attack is only possible from the back side. Why? Because Br is present on the front side and it is not possible to attack from the that side. Hence, there is result in the formation of a product where there is this inversion of configuration. Okay, so this means the configuration is completely changed. So this is how actually SN2 reaction happens. Now, the other point that you should remember in case of SN2 reaction is this. That is, this SN2 reaction is second order reaction. That's why it has got its name as what? Bimolecular. Why? Because we can see that the nature of my nucleophile is also very important along with the nature of substrate, because we know that primary alkyl halides are required. So if I take tertiary ones, they will not undergo SN2 reaction because of the huge hindrance near the carbon atom. Hence, the backside attack will not be possible. So the nature of the substrate is important. At the same time, the nature of the nucleophile is also important, because in order to have for this reaction to happen, we need a strong nucleophile that can easily attack and immediately form the product. So we need a strong nucleophile in order to do this reaction. So the concentration of the nucleophile as well as the concentration of the substrate is important. Hence, if we write the formula for the rate of reaction, this is what we get, the equation for the rate of reaction, and we can clearly see that rate is clearly dependent upon the nature of the substrate as well as on the nature of the nucleophile. So we can say that the order of this reaction is second order, and hence this reaction is called as what? Bimolecular reaction. Now, let us understand the reactivity order. So, if we have the primary alkyl halide, they will easily undergo SN2 reaction compared to secondary, compared to tertiary. And what's the reason? As you can see over here, if we have a primary alkyl halide, the backside attack is easily possible because of the less hindrance. Whereas in case of secondary, we can see that the hindrance is a little more. But as I told you earlier, there are few conditions that are required to be considered. So hence we will discuss about secondary in further slides. Whereas in case of tertiary, all three bulky groups are attached. Hence, it is not possible to carry out the backside attack, due to which only primary alkyl halides they are preferred for SN2 reaction. Now let us understand SN1 reaction mechanism. S where for in this abbreviation SN1, S stands for substitution, N stands for nucleophilic, and 1 stands for unimolecular reaction. Now you might have got the idea what is the meaning of this term unimolecular reaction. Well, it is absolutely right that unimolecular means only one molecule is involved in determining the rate of the reaction. So that's why we call it as what? SN1 reaction. Now let us understand the whole reaction. So this reaction consists of two steps, step 1 and step 2. Step 1 is the slow step and step 2 is the fast step. As you have studied in your inorganic concept, that whenever you have multi-step reactions, in those reactions, which one should we consider in order to determine the order of reaction? Well, always remember that you're going to choose the slow step, because out of all the step, whatever is your slow step, you're going to consider that step in order to determine the order of reaction. So as I can see, I have two steps, this step 1 and step 2. So out of these two steps, this first step is the slow one, and from this step I am going to determine the order of the reaction. So as I can see, only one reactant is involved, so my rate is dependent only on the one of the molecule, hence the order of the reaction is 1. So remember this point, that is the order of reaction for the SN1 is 1, because the rate of reaction is dependent only on the concentration of the substrate, not on the nature of nucleophile. I will also explain why it is not dependent on the nature of nucleophile. As you can see, in the first step, there is formation of a carbocation. This means first this Br, which is our leaving group, it is going to leave the substrate. As soon as it is going to leave the substrate, it is going to form the carbocation. As soon as this carbocation has formed, after this step, this OH minus is going to attack on this particular carbocation and results in the formation of the desired product. Now remember, since there is formation of a carbocation, this means attack is possible even with the use of uh, a weak nucleophile, and also if you use a strong nucleophile. There is no need to use a strong nucleophile, because even a weak nucleophile can easily attack, because it is a carbocation where the space is directly provided to attack for. So this means even if I use a weak nucleophile, it can easily undergo this reaction. Hence, there is no dependency of the rate on the nature of the nucleophile, because any of the nucleophile will give this particular reaction. But yes, the stability of the carbocation is of great importance, because if your carbocation is not that stable, it is not going to give a proper SN1 reaction. That's why we do not take primary alkyl halides, because in case of primary alkyl halides, we get primary carbocation which are least stable, and this tertiary carbocations, they are most stable. Hence we take these instead of primary. So I hope you have understood the difference. Why do we take tertiary alkyl halides in SN1 and why do we take primary alkyl halides in SN2? So these are the few points that I have discussed and which are very important for you to remember. Now let us understand the mechanism. So in first step, what happens? This Br, which is our leaving group, leaves the carbocation, leaves the substrate. As soon as this leaves the substrate, it results in the formation of a carbocation. Now, as soon as this carbocation has formed, the geometry of this carbocation is completely planar, as you can see over here. Since the geometry is completely planar, this means attack of that particular nucleophile is possible from front side as well as from back side. This means I will get two products, that is inverted product and also the retented product. This means there is inversion of configuration as well as there is retention of configuration. And whenever we have two different configurations substances together in a solution, we call that particular solution as what? Racemic mixture. Okay, so racemic mixture is a mixture of um, dextro and levo rotatory substances together in one solution is called as what? Racemic mixture. So remember that in case of SN1 reaction, we get both product, that is inverted as well as returned, and hence we say that at the end whatever is the solution that we have got is nothing but a racemic mixture. So this is how you're going to remember all the steps involved in the SN1 reaction mechanism. Now, this is the trick with which you can remember the most important key terms involved in SN1 and SN2. For SN2, remember this mnemonics, that is FBI1, where F stands for fast, B stands for backside attack, I stands for inversion of configuration, and 1 stands for the preference of the substrate that is going to undergo this particular reaction. And when we talk about SN1 reaction, the mnemonics is SBR3, where S stands for slow, B stands for both side attack, R stands for racemization. This means we get inversion and also retention of configuration together in one solution, and we call that resulting solution as what? Racemic mixture. And the process with which this happens is called as what? Racemization. And this 3 stands for the tertiary preference of the substrate in this particular reaction. So this is the easiest trick with which you will be able to remember all the important points, most important points which are required in order to explain SN1 and SN2 reaction along with its mechanism. Now the next topic is the reactivity order of halogen. So now here question arises, which halogens will react easily, or which halogens will easily undergo SN1 or SN2 reaction? Well, in both the nucleophilic substitution reaction, the requirement is that the leaving group should easily leave the substrate, because if the leaving group is going to leave the substrate easily, the substrate is readily available for the nucleophile to come and attack. This means I require a living group which can easily leave. So as you can see here, I have this order, and now we are going to reason why this order is given. So well, whenever we talk about a living group, these are the characteristic features that a living group has. Firstly, since the living group should leave easily, this means the bond that is formed with the carbon atom should be weak so that it can be broken easily. So when this bond is formed weak, when we have huge difference in the size of the atoms, or the orbitals which are getting overlapped. So we know that in case of carbon, this is what the orbital is, and the orbital of the carbon atom is smaller compared to the orbital of the halogen, specifically iodine. Okay, so when we have iodine, iodine is bulky in size, okay, compared to the carbon atom. So when these two orbitals, they overlap and form a bond, the bond formed between carbon and iodine is very weak, and hence the bond length is 2.14 angstrom. This means the bond is quite longer compared to the other bonds. This means this bond can be easily broken. Hence, the amount of energy required to break this bond is very less compared to the other halogens. So, in conclusion, I can say that iodine is the best living group because the bond formed with the carbon atom is very weak compared to the other halogen. So remember, whenever we have the reactivity order of halogen which undergo nucleophilic substitution reaction, the order is this. So why iodine easily leaves the substrate? The reason behind is its size, because iodine is bulkier in size, due to which the overlap of its orbital with the orbital of the carbon atom is very poor, due to which what happens, the bond formed is quite longer than that of the other halogen, and as the bond length increases, it is very easy to break the bond, and hence we require very less energy to break it. And we can say that if the bond is weaker, we can break it easily, and hence we can conclude that that particular group is a better living group compared to the other groups. So iodine is the best living group, and Br is the second one, and then Cl, and then fluorine. Okay, so this is how actually the reactivity order of halogens is. Now let us understand the most important topic, that is the factors affecting the rate of SN2 reaction. Well, there are four factors that can affect the rate of reaction. First one is the nature or the structure of the substrate. So when we talk about SN2 reaction, so in case of SN2 reaction, we know that there is backside attack that happens. So we need a substrate in a way that my nucleophile can come and easily attack the substrate from the backside. So I will prefer going with the primary alkyl halides than that of secondary than that of tertiary. So the preference order is that we usually prefer primary alkyl halides for SN2 reaction. Second is the strength of the nucleophile. So when I say strength of the nucleophile, remember in case of SN2 reaction, the order of reaction is 2, that is this reaction is bimolecular. This means the rate of the reaction is directly dependent upon the nature of the nucleophile and also the substrate. This means if I have a stronger nucleophile, it will attack easily because it has huge amount of electron density and can attack and can increase the rate of reaction. So I can say stronger nucleophile will give the faster reaction. Why? Because the rate is also dependent on the nature of the nucleophile. So if I take better nucleophile, stronger nucleophile, it will give me the faster reaction. Now the third is the nature of the leaving group. So as we have discussed just now in the previous slide, that iodine will be preferred compared to the other halogens. Why? Because suppose in the exam, if you're provided with two substrates, where in one, both of them they have the same number of carbon atom, both of them they are primary, and both of them they have the same nucleophile, then you will check for the leaving group. If one is having iodine and other one is having bromine, and you have asked to determine which one will undergo SN2 reaction easily, then you will blindly mark on the option where iodine is mentioned. Why? Because iodine forms a poor or the longer bond with the carbon atom, hence we can easily break that bond and iodine can easily leave the substrate. So we can say that that particular group is this particular this particular living group is better compared to the other ones. So remember these points because there are questions that are based on the factors affecting the rate of reaction. Now the next factor is the nature of the solvent. Yes, you're right, you might have not heard of this, but yes, the nature of solvent also affect the rate of reaction in case of SN1 and also in case of SN2. Remember, whenever we have polar aprotic solvent, that particular solvent is going to prefer SN2 reaction. Now let us understand why. When I say use this term polar aprotic, so this term gives a hint. Polar means such a molecule in which there are partial charges, and aprotic means it is not having a proton. Okay, which proton am I talking about? That proton is the acidic proton. What do you mean by the term acidic proton? Such a hydrogen atom which is directly attached to strongly electronegative atoms like oxygen, nitrogen, and fluorine. That particular hydrogen is called as the acidic hydrogen. Okay, so if we do not have that particular hydrogen present in our molecule, we call it as what? Aprotic. So if our solvent is polar and also aprotic, like for example acetone and DMSO. What do you mean by DMSO? Dimethyl sulfoxide. So as you can see here, I have dimethyl sulfoxide and here I have my partially positively charged primary alkyl halide carbon. So as you can see, this particular DMSO, it is going to surround this particular carbocation, only the oxygen part, and this particular nucleophile is completely free. Why? Because there is no proton with which it can interact with. So hence this nucleophile is readily available for the attack, and this is what we need, because if we have to increase the rate of SN2 reaction, we need a stronger nucleophile. So suppose if the solvent solvent that you have used, it has a proton, then this nucleophile is going to interact with that proton and is not available to attack the substrate. So in order to avoid such conditions, what do we have to do? We have to take such a solvent which should not have a proton, so that our nucleophile should not interact with that particular proton, and instead it it is not having any other option than attacking the carbon. So this is how actually the nature of the solvent comes in picture. So remember that nature of the solvent also matters in case of SN1 and SN2. So in order for SN2 to happen, we need a polar aprotic solvent. Polar means the substrate, the solvent molecules should have the partial charges, and aprotic means they should not have an acidic proton. Now let us understand the factors that affect the rate of reaction in case of SN1 reaction. The first factor is the structure or the nature of the substrate. So we know that in case of SN1 reaction, tertiary carbocations or the tertiary alkyl halides can easily undergo SN1 reactions. Why? Because they involve formation of an intermediate. Their intermediate is nothing but a carbocation, which can then be easily attacked by a nucleophile in order to form the desired effect. So remember that SN1 requires a stable carbocation, and this carbocation is stable because it has more substitutions, and these substitutions provide more plus I effect, that is positive inductive effect, which stabilizes the carbocation. Now the next factor is the nature of the leaving group. So as we have discussed that iodine is going to be the better leaving group compared to bromine, compared to chlorine and then fluorine. Why? Because if we have a longer bond, that bond can be easily broken and the reaction can further proceed easily. Now the next is the nature of solvent. As we know that in case of SN2 reaction, we require polar aprotic solvent, whereas in case of SN1, we require polar protic solvent. This means our solvent molecules should have partial charges. Along with that, it should have an acidic proton. So here I have taken an example of water as a solvent. As you can see, water is a molecule which is polar in nature because it has partial positive charges on hydrogen and partial negative charges on oxygen. So when this reaction of SN1 happens, we have formation of our carbocation, and as you can see that this carbocation is surrounded by the negative charge of these oxygen atoms, which are actually helping to interact and stabilize the carbocation, whereas the negatively charged leaving group, okay, negatively charged leaving group is surrounded by the partial positive charges of these protons which are present in water molecule. So what is happening is, since our leaving group is also occupied and interacts with the protons, it is not going to interact with the carbocation. So our carbocation is completely free and freely available for the attack by the nucleophile. So this means this chlorine is not going to interact with this carbocation at all. So that's why we need a polar protic solvent in order to carry out SN1 reaction. Then the last factor is the nucleophile. So as I told you that here the rate of reaction is not at all dependent on the nature of the nucleophile. Hence, even if we take the weak nucleophiles are enough in order to carry out this particular reaction. Now, after we have completed understanding SN1 and SN2 reaction in case of primary and secondary alkyl halides, primary and tertiary alkyl halides respectively. Now, let us understand secondary alkyl halides. Well, the reaction of these secondary alkyl halides depends upon two conditions. First one is the nature of nucleophile, second one is the nature of the solvent. So, if you have strong nucleophile, then this secondary alkyl halide will undergo SN2 reaction. If you have weak nucleophile, then this secondary alkyl halide will go SN1 reaction. Now, when you're going to, like suppose whenever you're having your question, which factor will you give the priority first? Well, you have to always remember that nature of solvent is on the higher priority than that of the nature of nucleophile. You will understand this point when I'm going to solve one question in the further slide. Here's the trick to remember which ones are strong nucleophile and which one are which nucleophiles are weaker one. So whenever we have a strong nucleophile, it should have a negative charge. It should be less electronegative atoms and it should be smaller in size. Because when we have these characteristic features present, then that particular nucleophile is called as what? Strong one. And when we have these kind of nucleophiles, we call them as what? Weak nucleophiles. Now, this is the very important rule that you should remember. Whenever you're going to decide whether the secondary carbocation is undergoing SN1 or SN2, you are going to follow this order in order to decide the right answer. Firstly, you will give the preference to the substrate, nature of the substrate. So here we are considering secondary alkyl halide. Now, since in both the cases I have secondary alkyl halide, the second preference I will choose is the solvent. Okay. So if I have polar aprotic solvent, then surely I will show SN2 reaction. If I have polar protic solvent, then I will surely show SN1 reaction. And suppose if the solvent is same in both the cases, then you will check for the nucleophile. This is what the order you're going to follow. Now, here is the first question that we have. Which of these compound would act as a nucleophile? Well, it is very easy to understand from this. We have this slide that we have discussed, so we can clearly see that OH minus clearly matches with the condition required for a nucleophile to be, and that's why we consider it as what? The nucleophile out of all three. Well, why not others are nucleophile? Because C2H6, it is not even having lone pair, no charge, so it is not a nucleophile. H plus, it is electron deficient, and we know that nucleophiles are the ones which get attracted towards a positive charge, so they should have either lone pair or negative charge. So this is not going to be a nucleophile. In case of aluminum, it is also electron deficient species, and also it is not going to get attracted towards the nucleus. Instead, it is going to get attracted towards the electrons. So it is not a nucleophile. So this means the correct option is this. Yeah. Now let us solve question number 2. So in this question, we are asked which reaction is an example of nucleophilic substitution reaction. So here we have these 4 reactions and we have to determine which one of them is a nucleophilic reaction. Now let us first look at A, B and D options. So in A, we have this benzene ring, and in this benzene ring we are adding bromine. So whenever we have benzene and there is a substitution of any of the group, we call that particular reaction as what? Electrophilic substitution reaction. We'll learn about this in detail in the next session. So this means A is absolutely not a nucleophilic reaction. Now option B. B is what? As you can see here, we have ethene and we are adding HBr to it. So we have learned in the previous session that whenever we add HBr to ethene, this reaction is nothing but an addition reaction. So this means B is not also a nucleophilic reaction. Now option D. So here we have ethane and we are adding bromine. So whenever we add any halogen to an alkane, we call it as what? Free radical substitution reaction. This we have learned in the previous session. So this means option D is also not the correct option. So we are left with the option C. So here we can see that we have bromine which is acting as a living group, and we have water which is acting as a nucleophile. And you can see here is how the reaction happens between both. So we can conclude that this option C is a nucleophilic substitution reaction. So this is the correct answer for this question. For this is this. Now let us solve this question 3. Which factors affect the rate of nucleophilic substitution reaction in halogen alkanes? So here are 3 factors given and we have to identify which of these are the factors which actually affect the rate of nucleophilic substitution reaction. So in the previous slides, we have discussed that there are four factors that affect the nucleophilic substitution reaction. First is the nature of the substrate. Second is the nature of the living group. Third is the nature of the nucleophile. Fourth is the nature of the solvent. So I can see that out of these four, these three are mentioned. That is the nature of the attacking nucleophile, the structure of the substrate, the identity of the halogen. Okay, so this means identity of the halogen means the nature of the living group. So all these three factors affect the nucleophilic substitution reaction. So the right answer is this option D. Now here is question 4. In the hydrolysis of bromoethane by aqueous sodium hydroxide, what is the nature of attacking group and of the leaving group? So well, when we talk about a nucleophilic substitution reaction, as you can see here, I have bromoethane, and here I'm talking about the nucleophilic substitution reaction. So this is the nucleophile, because when I have sodium hydroxide, I have Na plus and OH minus. So this OH minus will act as my nucleophile. So this nucleophile is going to attack this particular carbon atom over here, and this bond is going to break. So I can see that OH minus is my nucleophile, and that is, this is my attacking group, and this Br is my leaving group. So I can see that Br is also negatively charged, and we have learned about this. Whenever a species is having a negative charge or lone pair, we call that particular species as what? Nucleophile, because they are nucleus loving. So I can say that in conclusion, attacking group as well as the living group, they both are nucleophile. So this option is correct. Now this question is for you to solve. So do solve this question and answer your whatever is your answer, comment it in the comment section. I will surely reply to it. If you have any query, you can also mention that in the comment section. Now this is our question 6. But1 ene is reacted with first with hydrogen chloride to produce X, which is then reacted with aqueous sodium hydroxide to give Y. Finally, this Y is reacted with excess acidified potassium dichromate solution. So here I have my alkene, and it is going to react first with what? HCl. And we are getting some product as what? X. And then this X is reacting with aqueous NaOH, and we are getting our product as what? Y. Then finally it is reacting with this reagent, that is acidified potassium dichromate. I will tell you what is the function of this particular reagent in the next slide. Then it will give what? Z. So we have to predict what is the probable structure of this Z out of all these four options. So let us solve this question by breaking it down into the steps, okay, simpler steps. So here I have an unsymmetrical alkene which is reacting with HCl. So this is my first step, which is nothing but the addition reaction of HCl, which is following what? Markovnikov's rule. Why? Because whenever we have an unsymmetrical alkene and there is addition of HCl or HBr, okay, but in case of HBr there is no peroxide, then only we are going to follow what? Markovnikov's rule. So what Markovnikov's rule says, it says that the negative part of the reagent, so here in this case it is Cl, it is going to get added onto the carbon which has less number of hydrogen atom. So when this particular we are adding this particular reagent to this unsymmetrical alkene, this is what the product we get, because this carbon has more hydrogen than that of this carbon. So we are going to add Cl to this carbon and hydrogen to this carbon. So this is what the product we get, and I have named it over here as what? 2-chlorobutane. Now this 2-chlorobutane is reacted with NaOH, which is in aqueous solution, which is nothing but water. So here it is going to follow what? Nucleophilic substitution reaction, because this OH present in NaOH will act as what? A nucleophile, and it is going to substitute this particular chlorine. Now here the question arises, since I have secondary alkyl halide whether this reaction will follow SN1 or SN2. Well, in that case, you're going to follow this rule. So here I can see that the nucleophile is strong. But as I told you earlier, whenever you're going to check for secondary alkyl halide, always give preference or the priority to the solvent then the nucleophile. So let us check what type of solvent we have over here. So here we have water present in this particular solution. So water is a polar and protic solvent. So when we have polar and protic solvent, always that particular reaction is going to follow what? SN1 mechanism. So giving preference to the solvent over the nucleophile, this even if the nucleophile is strong, this reaction is going to follow what? SN1 reaction mechanism. Why? Because this particular solvent is going to stabilize the carbocation and the leaving group. Hence, the reaction is favorable towards the SN1 reaction. Now, the next step is this. After getting this particular product, that is nothing but uh, this particular product, let us react it with what? Acidified potassium dichromate. So what is the function of this acidified potassium dichromate? Well, it acts as an oxidizing agent. So it oxidizes this particular alcohol into ketone. So remember that whenever you have when we have primary alcohols, it is going to form aldehyde. When we have secondary alcohol, it is going to form what? Ketones. And also when we have tertiary alcohols, it is also going to form what? Ketones. So this is what you have to remember. So in conclusion, we can say that there is formation of what? Ketone. So that's why this option B is correct. So this is how you're going to solve such questions. So with this, we have completed our session. Thank you so much for watching. Do like, share and subscribe to our channel Artistic Atom. See you in the next session.